A relation is a table that holds data. Think of the table as a set of columns, attributes like A, B, C. A functional dependency, FD, X arrows Y means, if you know the values of the columns in set X, you can always figure out the values of the columns in set Y. A candidate key is the smallest group of columns that can uniquely identify every row. BCNF rule in simple words. For every non-trivial FD, X arrows Y that holds in the table, the left side X must be a superkey, a set that contains a candidate key. For all X arrows Y in F+, X not equal to empty set, Y not subset of X implies X is a superkey of R. If any FD breaks this rule, the table is not in BCNF. In child-friendly terms, imagine a school class list where each student has a unique ID. The rule says, whenever a piece of information, like student name, can be determined from some columns, those columns must already be enough to tell you exactly which student you are looking at. If you need extra columns that are not a unique identifier, the rule is violated. Explanation: to see whether a table breaks the BCNF rule, we use the closure of an attribute set. The closure X plus is the set of all columns we can figure out if we start only with the columns in X and repeatedly apply all known functional dependencies. Step-by-step check. 1. Pick a functional dependency X determines Y that is not trivial. Y is not already in X. 2. Compute X plus using all functional dependencies in the schema. 3. If X plus contains all attributes of the relation, then X is a superkey, and the functional dependency is okay for BCNF. 4. If X plus does not contain every attribute, the functional dependency is a BCNF violation. Analogy: imagine you have a box of Lego bricks attributes. You know some building rules, functional dependencies. Starting with a few bricks X, you try to build as many other pieces as possible, closure. If you can build the whole model, all bricks X was powerful enough, a superkey. If you cannot finish the model, you need more bricks, meaning the rule X determines Y breaks BCNF. The closure operation is performed by repeatedly adding any attribute Z, such that there is a functional dependency A determines Z with a already in the growing set, until nothing new can be added. Explanation: when a table is not in BCNF, we can decompose it into smaller tables that are. The goal is a lossless join. After the split, we can put the pieces back together and get exactly the original rows, no extra or missing rows. BCNF decomposition algorithm, simple version. 1. Start with the original relation R and its set of functional dependencies F. 2. Find a violation. Locate a functional dependency X determines Y where X is not a superkey. 3. Create two new relations. R1 equals X union Y, all attributes that appear in the violating functional dependency. R2 equals R minus Y minus X, the original relation minus the attributes that depend on X but keep X. 4. Replace R in the schema with R1 and R2. 5. Repeat steps 2 through 4 for each new relation, until every relation satisfies the BCNF rule. 6. Stop when no more violations are found. Why it works: the intersection of R1 and R2 is exactly X. And because X determines Y holds, the join on X will never create extra rows, that is the lossless join property. Kid-friendly picture: think of a pizza cut into slices. If a slice has toppings that belong together like cheese and tomato, you keep them together, R1. Anything else goes in another slice, R2. When you put the slices back, you still have the whole pizza exactly as before. The algorithm guarantees that each resulting table is in BCNF, and that you can reconstruct the original data without loss. Lossless join: we already saw that the algorithm keeps a common attribute, the left side X of the violating functional dependency. Because X uniquely determines the removed attributes, joining the pieces on X brings back exactly the original rows. No phantom rows appear. Dependency preservation: after decomposition, we would like to keep all the original functional dependencies so that we can enforce them without having to look at several tables at once. Unfortunately, BCNF sometimes forces us to drop this property. Some functional dependencies may be split across two tables, meaning we would need to join the tables just to check the rule, which is costly. Example: suppose we have functional dependencies A determines B and B determines C. After BCNF decomposition, we might end up with tables R1 parentheses a comma B parentheses and R2 parentheses B comma C parentheses. The functional dependency A determines C is not preserved in a single table. To verify it, we would have to join R1 and R2. Analogy, think of a library rule. If a book is a picture book, it must be in the children's section. If you split the catalog into one list for picture books and another for sections, you can still see each rule separately. But the combined rule, picture books determines children's section, now lives across two lists, making it harder to enforce directly. In practice, designers often accept a small loss of dependency preservation to achieve BCNF, because the lossless join guarantee is more critical for data integrity. 3NF third normal form and BCNF are close cousins, but they differ in how strict they are. Rule for every FD, X determines Y. Either X is a superkey or each attribute in Y is part of a candidate key. That is, Y is prime. Rule for every FD, X determines Y. X must be a superkey. Typical violations allows FDS where the dependent attribute is itself a key attribute prime. Typical violations disallows any FD where the left side is not a superkey even if the right side is prime. Resulting schema size, usually fewer tables, often preserving all dependencies. Resulting schema size may create more tables, sometimes losing some dependencies. Practical impact, easier to query because fewer joins, good for many business apps. Practical impact, cleaner design with less redundancy, useful when update anomalies are a big worry. Real-world picture, imagine a school database where each class has a teacher and each teacher has a department. The FD teacher determines department has a non-key left side, but department is a key attribute of the department table, a prime attribute. 3NF would allow keeping all three columns in one table, but BCNF would split the teacher-department relationship into its own table to avoid any chance of inconsistency. Kid analogy, 3NF is like saying, you can keep your socks and shoes together as long as the shoes are a special kind that always match the socks. BCNF says, never keep socks and shoes together unless the pair itself can uniquely tell you which person they belong to. Thus, BCNF is a stricter, more pure form of normalization. Designers choose BCNF when they need the strongest protection against update anomalies, and they accept the extra joins or possible loss of some dependencies. Original schema, course enroll student ID, course ID, instructor, room, time. Assumed functional dependencies. Functional dependency 1, student ID and course ID determine instructor, room, and time. A student enrolls in a course at a specific schedule. Functional dependency 2, course ID determines instructor, room, and time. Each course has a fixed instructor, room, and time. Functional dependency 3, instructor determines room and instructor always teaches in the same room. Step 1, find candidate keys. Using functional dependency 1, the pair student ID and course ID determines all other attributes. So the set student ID, course ID is a candidate key. No single attribute determines everything, so the only key is student ID, course ID. Step 2, check Boyce-Codd Normal Form. Functional dependency 2 has left side course ID which is not a superkey. It does not contain student ID violation. Functional dependency 3 also violates Boyce-Codd Normal Form because instructor is not a superkey. Step 3, decompose on functional dependency 2. Create relation R1 with attributes course ID, instructor, room, time. Create relation R2 with attributes student ID and course ID, the remaining attributes plus the left side course ID. Now examine each new relation. Relation R1 still has functional dependency 3, instructor determines room, and its candidate key is course ID. Functional dependency 3 again violates Boyce-Codd Normal Form inside relation R1, because instructor is not a superkey of R1. Step 4, decompose R1 on functional dependency 3. Create relation R3 with attributes instructor and room. Create relation R4 with attributes course ID, instructor, and time. Keep course ID and the attributes not in the violating functional dependency. Resulting Boyce-Codd Normal Form schema. Relation R2 with attributes student ID and course ID. Key is student ID, course ID. Relation R3 with attributes instructor and room, key is instructor. Relation R4 with attributes course ID, instructor and time, key is course ID. Verification. In each relation, every functional dependency left side is a superkey, so all are in Boyce-Codd Normal Form. The join of R2, R3, and R4 on the common attributes course ID and instructor is lossless because the intersections are keys. What we did mathematically, we computed closures to see which attributes each left side could determine. We applied the decomposition rule. Relation goes to X union Y, and relation goes to R minus Y minus X. Kid story, think of a school schedule as a big Lego set. Some pieces, the course code, tell you everything about a class, but other pieces, the teacher, only tell you part of the story. We split the set into 3 smaller boxes, one that matches students to courses, one that matches teachers to rooms, and one that matches courses to teachers and times. Each box now holds pieces that fit together perfectly, so we never get a mismatched schedule. The step-by-step calculations above show exactly how we used closures, and the Boyce-Codd Normal Form algorithm to reach a clean design. When deciding whether to push a database design all the way to BCNF, ask yourself these practical questions. How likely are update anomalies? If the same piece of information, for example an instructor's office, appears in many rows and could be changed independently, BCNF helps avoid inconsistencies. How costly are extra joins? BCNF often creates more tables, so queries may need more joins. If the workload is heavy and performance is critical, you might stay in 3NF. Do you need all functional dependencies preserved? If business rules must be enforced directly by the database management system without extra code, and the BCNF decomposition would break them, you may choose 3NF. Size and complexity of the schema. Small schemas are easy to keep in BCNF. Huge schemas may become unwieldy. Tool support and developer expertise. If the team is comfortable with writing joins and maintaining integrity in application code, BCNF is fine. Otherwise, a simpler normal form may be safer. Regulatory or auditing requirements. Some domains, for example finance or healthcare, demand the strongest guarantee against redundant or contradictory data, nudging designers toward BCNF. Decision flow simple. Start with 3NF, most designers do this automatically. Look for any functional dependency where the left side is not a superkey. If such a functional dependency exists and the data it protects is critical, perform the BCNF decomposition. Re-evaluate query plans. If performance degrades, consider denormalizing selectively, adding back some redundant columns, but keep the core in BCNF. Everyday analogy, imagine you are organizing a toolbox. 3NF is like grouping tools by type, screwdrivers together, hammers together, even if some screws end up in multiple boxes. BCNF is like ensuring each specific screw type lives in only one box, even if you have to create a new tiny box for a few rare screws. You choose BCNF when you don't want to lose a screw or put the wrong one with the wrong tool. Explanation: putting a schema into BCNF changes how the database works under the hood. More joins, potential slower reads. Because data is spread across more tables, select statements often need extra join operations. Modern DBMS can optimize joins, hash joins, merge joins, and use indexes to keep the cost low. Better write performance, updates, inserts, and deletes touch fewer rows because redundant data is eliminated. This reduces lock contention and write-ahead log overhead. Indexing strategy. Since each BCNF table has a clear primary key, the superkey that appears on the left side of the FD, you typically create a primary key index on that column S. For foreign key relationships created during decomposition, you also add indexes on the referencing columns to speed up joins. Cache efficiency, smaller, well-structured tables fit better in memory pages, leading to fewer page reads. Query planner hints. Some DBMS let you hint that a join is known to be lossless. The optimizer can then skip certain duplicate removal steps. Kid metaphor. Think of a bookshelf where each book lives in exactly one shelf. BCNF finding a book may require walking to a different shelf, extra step. But when you need to change a book's title, you only edit one copy. Never worry about forgetting to change it elsewhere. Practical tip. After moving to BCNF, run the query workload with an explain plan. If a particular query becomes too expensive, consider adding a covering index or, in rare cases, denormalizing that specific piece of data, keeping a duplicate column while still keeping the rest of the schema in BCNF. Explanation::BCNF is powerful, but it is not a silver bullet. Here are the common trade-offs. Potential loss of dependency preservation. As shown earlier, some functional dependencies may be split across tables, meaning the DBMS cannot enforce them automatically. You may need application-level checks or additional triggers. More tables leads to more joins. Extra joins can hurt read performance, especially for complex reports that need many attributes from different original tables. Design complexity. Understanding and applying the BCNF algorithm requires a good grasp of closures and candidate keys, which may be challenging for junior developers. Redundancy versus performance. In some cases, keeping a small amount of redundancy denormalization yields faster queries. Designers must balance the pure normalization goal with real-world performance needs. Maintenance overhead. More tables mean more schema. Objects to document version and backup. Real-life story: a large e-commerce site initially normalized everything to BCNF. They later discovered that order summary pages required joining 5 tables for every page view, causing latency spikes. The team introduced a materialized view that stored a pre-joined snapshot of the most used columns. The core database stayed BCNF, but the view added a controlled amount of redundancy for speed. In short, BCNF gives you the strongest guard against anomalies, but you may sacrifice simplicity and query speed. Good designers weigh these factors and sometimes keep a hybrid design: core tables in BCNF, selective denormalized tables or views for heavy read paths. Modern database tools can help you check whether a schema is in BCNF and, if not, suggest a decomposition. Here are some common ways to automate the process. Schema design IDEs. Tools like Studio, IBM InfoSphere Data Architect, and Oracle SQL Developer Data Modeler let you draw entities, define FDS, and then run a normalization wizard that reports BCNF violations and produces the decomposed set of tables. Command line utilities. Open source projects such as dbnorm-python and fdtool. Java accept a list of attributes and functional dependencies, compute closures, candidate keys, and output whether the relation is in BCNF. They can also output the step-by-step decomposition. SQL-based scripts. You can write stored procedures that read metadata from information schema column definitions, foreign keys, and using a built-in FD inference engine, e.g. in PostgreSQL PG, normalize extension test for BCNF. Academic libraries. The FAI Functional Dependency Analyzer library for Haskell and the normalization module in the CMPy library provide programmatic functions like is_BCNF and BCNF decompose. DBMS built-in features. Some commercial systems, e.g. Microsoft SQL Server with Database Diagram Designer, can highlight redundant columns and suggest normal forms, though full BCNF checks often require third-party plugins. How to use them: simple steps. List all attributes of each relation. Write down all known functional dependencies, often derived from business rules. Feed this information into the tool. Review the generated report. It will list violating FDS candidate keys and a series of new relation definitions. Apply the suggested schema changes to your DDL. Create table statements. Child analogy. Think of a spell checker that not only points out misspelled words violations, but also suggests the correct spelling and rewrites the whole paragraph automatically. These tools are the spell checkers for database design, making BCNF easier to achieve without doing all the math by hand.